So this lecture is mostly, in a sense, preparation for next week when we return to the main topic of Hilbert schemes. What I want to explain is one of the basic tools in geometric representation theory, by which I mean the geometric construction of representations of algebraic things, which is the idea of correspondences, particularly how correspondences give rise to operations on homology. So the motivation for this is something like the following. If you have a continuous map of topological spaces, then we all know that it induces maps on homology, push-forward maps, which are usually written F lower star, from the homology groups of X to the homology groups of Y in the same degree. And for some purposes, that's what you want. So this implies, for instance, that if a group G acts on X, then it also acts on the homology of X. So that's a way of producing linear representations of a group if you have an action of it on a topological space. So that may or may not be interesting, but that's one thing that you get from the functoriality of homology. But it's not flexible enough for all circumstances. And in some situations, what you want is something more, something that really takes advantage of the flexibility of homology as compared to actual topological spaces and continuous maps. So with the sort of situation I have in mind is that you have a closed subset of the product of X and Y, which is not necessarily the graph of a morphism of a continuous map. So the previous case would be represented here by the case where Z was the graph of F. But suppose you have some closed subset of the product that's not necessarily the graph of a map. Maybe under some circumstances that will still induce some map on homology from X to Y. So the idea is that we want to find what circumstances that would be true. And you would sort of hope that, or at least the general pattern that occurs in a lot of cases is that if you consider the two projection maps from Z to X and to Y, say P sub X and P sub Y, you would like to construct a map from homology of X to homology of Y, which is essentially pullback followed by push forward. So you'd like to say that you can first pull back through the projection to X and then push forward through the projection to Y. And that's how your closed subset Z defines a map from the homology of X to the homology of Y. But the problem here, of course, is that this pullback doesn't generally make sense. So this is not usually defined if you're talking about homology. Homology is a covariant functor. It has push forwards, and ordinarily the thing you think of as having pullbacks is cohomology, the contravariant functor, the dual of homology, at least if you're working with fields with complex coefficients. So what we really want is a homology theory which is sort of a bit of a mix of covariant and contravariant, which has both push forwards and pullbacks. It's implausible for it to have push forwards and pullbacks with respect to all maps. So what you give up is that complete functoriality property Instead, what I'm going to describe is that in a suitable homology theory, you can have push forwards with respect to some maps and pullbacks with respect to some maps, and that's enough to make this sort of diagram and construction make sense with some assumptions on the set X and on the spaces X, Y, and Z, and these maps. So the theory which is normally used in geometric representation theory for these purposes is Borel-Moore homology. So this is it's also known as locally finite homology. And the first half of today will be essentially just an introduction to some of the basic properties of Borel-Moore homology. Firstly, I'm always going to be considering homology with C coefficients. So ordinarily, when you don't specify the coefficients, it means the coefficients are Z, but in this talk, the coefficients will be C. I am only going to consider fairly nice topological spaces. So to say what I mean, I guess, so some standing conventions about spaces will be that manifold means connected oriented manifold. Finite dimensional, in case that isn't included in the definition of manifold. The primary examples of manifolds when I actually apply this theory later on will actually be smooth varieties over the complex numbers. So if V is a smooth, irreducible variety of dimension D over C, then the set of C points of V with strong topology is a manifold of dimension 2D. Over R. The canonical orientation comes from the complex structure. And I actually, in practice, won't actually make a distinction between the original variety and its set of C points with the strong topology. So in practice, I would just still call this V. Okay, so the manifolds are the nicest spaces we'll consider, and those include the smooth complex varieties, but we'll also need some singular complex varieties. So those as topological spaces are not quite as nice as this, but they're still pretty nice. So the standing assumption on topological spaces in general will be that they have to be they have to have a nice closed embedding in a manifold. Manifold as defined on the other board. So what I mean by nice is that so this space is a closed subset of a manifold in such a way that it's a proper deformation retract of a closed neighborhood. So this is a technical condition which is needed to make the definitions work, but we don't need to care about it because it's a known fact that for any, well, and I'll say V again, for any variety over the complex numbers, if you take its set of C points with the strong topology, then it is a topological space of this kind. So if V is quasi-projective anyway, this is fairly clear because by definition, then V is a locally closed subset of a projective space, and complex projective space is a manifold. So you can use that embedding as the embedding you're talking about, and then it's a fact that this is always a nice embedding in this sense. So it's, this assumption on the space has various consequences for the topology. For instance, it implies that the space is Hausdorff, locally compact, paracompact, various other nice things like that. And I'll refer you to the book by Chris and Ginsberg in the section where they introduce Borel-Moore homology there. They go through the various topological properties that are involved in the definition. So this is going to be a homology theory which is at least well adapted to our purposes in the sense that it covers, the spaces that it covers include all varieties over the complex numbers. Okay, so then once you have this set up, what is Borel-Moore homology? So firstly, the ordinary homology. So let X be a space, and for some things later, I'll need the embedding of X in a manifold N, but not at first. So the ordinary homology H dot of X. This is by definition, the homology of the chain complex of singular chains. Okay, the definition you can find in any algebraic topology book. And in the ordinary setting, Ci of X means the vector space of finite linear combinations of singular I chains. X, so continuous maps from an I simplex to X. And what you change for Borel-Moore homology as the alternative name of locally finite homology suggests, you just change finite linear combinations of singular I chains to, sorry, I didn't mean to say I chains, I meant singular I simplices, I guess. Right, the chain is a linear combination of simplices. Yeah. Okay, sorry. You just change finites to locally finite. I might write LF for locally finite. This is locally finite linear combinations of singular I simplices. So what does locally finite mean? It means, so you have some infinite formal linear combination of simplices, and it has to be locally finite in the sense that every, well, for every point in X, there is a neighborhood of X which meets only finitely many of the simplices with non-zero coefficients. So it seems like a fairly minor change to the definition, just allowing some infiniteness, but infiniteness not in a not visible in a small local patch, just sort of some global infiniteness. But it has major, well, it makes major changes to the to what this is. And in particular, this change is enough for it to stop being a homotopy invariant. So a lot of the familiar properties of homology go away, are lost after this modification. So the easiest way to see that is to think of a basic example. So I should actually maybe write this down as a warning, first of all, that Borel-Moore homology is not an invariant of topological spaces up to homotopy. As this example shows, you can have interesting Borel homology of contractible spaces. So if you just take X to be R2, or if you want to think of this as a complex variety, you can think of it as a complex affine line. And then if you have the ordinary homology groups of R2, of course, is, so I'm taking C coefficients. So it's one dimensional if in degree 0 and 0 otherwise. But I claim that the Borel-Moore homology groups are different. In fact, they can detect the fact that R2 is two-dimensional. So you get non-zero homology in degree 2 and 0 otherwise. So to see that in terms of the chains, you can think of the following locally finite chain. If you just take the plane and triangulate it, tile it with triangles in some way like this, then that tiling of the plane by triangles is, I mean, then if you just take each triangle with coefficient 1, that is a locally finite linear combination of triangles in the plane. And this, it's easy to see that this is not a boundary. of any three chain, and its boundary is 0. If you take the boundary of each triangle, then you'll get every one of these edge segments both with a plus sign and a minus sign. So and so this is a cycle. So this generates the non-zero H2 Borel-Moore homology of R2. And if you think about what generates the non-zero the ordinary H0 here, you could just take the class of a point. So this generates H0 because its boundary is 0 by definition, and it's not the boundary of anything because, well, it's a single point. But in Borel-Moore homology, a point is the boundary of something. If you have a point like that, well, so if that's your special point, that's the boundary of an infinite but locally finite chain where you just have a collection of line intervals going on forever. So since that's allowed in Borel-Moore homology, a point suddenly now becomes a boundary. So this point here. So that's why you don't get an, so that's why H0 in Borel-Moore homology is 0.
Anthony, can I just ask a question?
Yeah, Josh.
Yeah, so in this situation, is there a natural type of invariance you can associate between homotopy invariance and homeomorphism invariance for this thing?
So Josh is asking if there's a natural equivalence relation between homeomorphism and homotopy for which this homology group is an invariant. So that's a good question. I think I hadn't thought of any specific thing to say about that, but I think it will be in a sense answered by what I'm about to say next, where I explain how to interpret Borel-Moore homology in terms of the traditional homology and cohomology groups of pairs. Yeah, so you know, if you're sort of wondering why this definition isn't in Hatch's textbook or something, it actually is, but it's in one of the exercises. It's because this is not really something new. It's something which you can interpret in terms of ordinary homology and cohomology. So specifically, the relationship is like this. So I'll be stating various facts without proof about Borel-Moore homology, and most of them are explained in the Kristen Ginsburg textbook. So firstly, if you happen to be talking about a compact space, then you can show that the Borel-Moore homology is the same as the ordinary homology. So my example of where they differed with the plane certainly very much used the fact that the plane was escaping to infinity. And if you can show that if your space is compact, then you can reformulate the locally finite chains in terms of finite chains. And I mean, you can show that it makes no difference to the homology of that complex. And if X is not compact, then actually the Borel-Moore homology is still just ordinary homology, but not of X, rather of the one-point compactification and relative homology of the pair where X tilde is the one-point compactification of X. So as I said, it's X with an extra point at infinity. So actually Borel-Moore homology is an example of relative homology, define it that way. What's actually more useful for our purposes is that an interpretation of Borel-Moore homology in terms of cohomology using the manifold M that it's embedded in. So let's say that the dimension of the manifold is lowercase m, then this Borel-Moore homology is actually canonically isomorphic to the m minus ith cohomology group, relative cohomology of M, where the pair is M and then the complement of X in M. So in other words, since I'm talking about C coefficients, cohomology is just literally the dual of homology. So what this is saying is that there is a perfect pairing between the ith Borel-Moore homology of X and the M minus ith relative homology of the pair of M and the complement of X. So a pairing between these two vector spaces, which puts them in duality, so that the Borel-Moore homology is isomorphic to the dual of this relative homology. And it's just given by intersection, so to speak. I put intersection in inverted commas because you have to interpret intersection in a suitably topological way. You have to sort of so if you have a chain here in X and a chain here in M, where now you're incorporating the condition that you're sort of ignoring information that's happening outside X, then you can intersect those chains in the sense that you may have to perturb them a bit first to get a generic position, and then count intersections between the I-dimensional simplices here and the M minus I-dimensional simplices here. And that's essentially how this pairing is going to be defined. But the details of it are a bit technical. So, but you can sort of see this in the example that I had on the previous board. So I might just move back to that board for the purpose of stating this example again. So this is a situation where you can take the manifold M to be the space X itself. So then you're not, in fact, dealing with a relative homology group. You're dealing with the ordinary homology of the space. And this is saying there's a perfect pairing between the ordinary homology HI of R2 and the Borel-Moore homology in the complementary degree, where you take 2 minus I instead of I. So you can see here that the places where this was non-zero matched up. Here you have it in degree 0, and here you have it in degree 2. And the claim is that those homology groups were always going to be in duality with each other because of this intersection, the possibility of intersecting. So here a 0 chain, just a point. Here this locally finite 2 chain, which is the tiling of the whole plane. You do literally intersect them, and this point lies on one of these triangles. So one of the simplices has a intersection number of 1 with this point, and the others have intersection numbers of 0. So the intersection pairing gives you a 1 between those two things. So you can sort of see again why you need things to be able to escape to infinity. In order to get a perfect pairing out of intersection like this. It wouldn't work if you were just using ordinary homology, because because you need to be able to move this point around. So it wouldn't be good enough to have a 2 chain which just consisted of a finite collection of triangles, because then the point could be moved outside the support of those triangles and they would have intersection 0. But now that you've allowed the support to be the whole plane, it's guaranteed to capture the point somehow. So all I'm saying is that for a non-compact space, homology is not in a natural duality with itself. But if you have a non-compact smooth space, homology is in a natural duality with Borel-Moore homology. Or in other words, the Borel-Moore homology is isomorphic to the cohomology in the complementary degree. Are there any questions about that?
Yeah, I'm wondering in the other board whether the n minus I is meant to be I or M. Yeah, I'm a bit confused. You're pairing Borel-Moore with ordinary homology of degree m minus I.
Yeah, so so in this pairing here, the idea is that the degrees should be complementary. I mean, essentially, if you have an I chain here, it's made up of I simplices, and you should be intersecting that with something m minus I dimensional so that you expect to get points.
Okay, and you're using Poincare duality here somewhere, right? For n?
Well, yeah. So, but it's asking about the connection between this and Poincare duality. So, if x was equal to m, if x was a self-smooth, then this is saying this is one way of saying Poincare duality. It's more traditional to actually replace Borel-Moore with ordinary homology here and replace this cohomology with compact supports here. Yeah, so I mean, somehow it's the same statement, but you just impose the finiteness or compactness condition on the other side rather than.
Thank you.
Yeah, thanks. Okay. So I was claiming that this would be a good thing to look at in order to construct correspondences for which we need pullbacks and push forwards. So we need to explore the functoriality of this Borel-Moore homology, and we've already seen it's not a homotop invariant, so it's not going to be quite as nice as ordinary homology in its properties. So firstly, in terms of push forwards, you don't get push forwards for arbitrary continuous maps anymore. But what you get is that if F is a proper continuous map, so in the topological setting, that means that the inverse image of compact sets is compact. And in the context of algebraic varieties, this is a property which is satisfied for projective morphisms, certainly. So it does come up in the context we're going to be applying this to. Then you get a push forward from the Borel-Moore homology of X to the Borel-Moore homology of Y. And this is functorial when restricted to the category of proper maps. So the push forward induced by the composition of two proper maps is the composition of the individual push forwards. It's relatively easy to understand why you have this sort of condition. When you define these push forwards, you want to take a chain in X and just map it under F to a chain in Y. And if your map is not proper, then that the local finiteness condition won't necessarily be satisfied. But if the map is proper, then for every point in Y, the inverse image is a compact set in X. So only finite, I mean, so since the chain here was locally finite, on this compact set, there'll be only finitely many simplices that you need to care about. So what you get here is still locally finite. Okay, so we do have push forwards, but only for proper maps. We also wanted pullbacks, and we have a chance for those given that we've seen that Borel-Moore homology is isomorphic to a cohomology group. So it is sort of going in the right direction. But we still don't get pullbacks because that involved the embedding into the manifold. We still don't get arbitrary pullbacks. What we get is as follows. So firstly, if you have an open subset of one of these spaces, and say you let F be the complementary closed subset, and I'll write U, lowercase u, for the inclusion of U in X, and lowercase f for the inclusion of capital F in X. Then you do get a pullback to an open subset. So a map, degree preserving linear map from the Borel-Moore homology of X to that of U. And moreover, this fits into a long exact sequence. And I can never remember which side is which. So the Borel-Moore homology of the closed subset, according to part 1, closed inclusion is certainly a proper map. So you get a push forward through F from capital F to capital X, and then you've got to pull back through U from capital X to capital U. And this is part of a long exact sequence with boundary maps. So now the next map would go to the I minus first Borel-Moore homology of capital F. Yes. So this is something that you don't have for ordinary homology, and it's somewhat of a pain. But for Borel-Moore homology, you do get this sort of optimal way of expressing the homology of a space in terms of the homology of an open subset and the complementary closed subset. So that's one kind of pullback map that you have, but that wouldn't be good enough to do much on its own. But another kind of pullback map where you can guarantee that the embeddings in the manifolds will get carried along is if you have a locally trivial fibration with fiber, which is the manifold. Of dimension m. So that's dimension over the reals. Then you get a pullback which changes degree. Goes from the ith Borel-Moore homology of Y to the I plus mth Borel-Moore homology of X. So to prove this, you have to show that you can extend this locally trivial fibration in some way to the ambient manifolds in which X and Y are closed subsets, are nicely embedded. And then it's just a matter of translating a known pullback map in the relative cohomology group that came up before. So that business about extending this fibration to the ambient manifolds is where you need the embedding to be nice, in the sense that I briefly mentioned before. You can't just take a random closed subset of manifolds and expect this to be true. Okay, so we've got at least some limited push forwards and some limited pullbacks. And the other main property we have as an intersection pairing. So if X and Y are both nicely embedded in the same manifold, then you get an intersection pairing, which is usually written with the normal cap symbol, but you have to write M as a subscript to remember what ambient manifold the intersection is being defined in. So it takes the ith Borel-Moore homology group of X and the jth Borel-Moore homology group of Y. So in some suitably topological sense, you're intersecting an I chain here and a J chain here. And what you get is an I plus J minus M chain in the intersection. Maybe you have to separately assume that the intersection is nicely embedded in the same M. I'm not sure that that actually follows from the statements for X and for Y. So this I plus J minus M is somehow the dimension you would expect the intersection to be if the intersection was transverse in some sense. So the proof of this again is just a matter of translating it into a statement about the relative cohomology groups of M, and there it translates into the cut product on relative cohomology. Just one more basic property, which is particularly nice. Kevin was asking before I erased U upper star whether it was going to be important. Maybe not this week. Sorry, the definition of U upper star is also just straight from known pullbacks in relative cohomology. So in that case, there's almost nothing to prove, because if X is nicely embedded in a manifold, then okay, so U is not a closed subset then. Maybe there is something to prove, sorry, yes, okay. But anyway, it again just comes from the cohomology interpretation of this Borel-Moore homology. So I guess this would be number 5. It's slightly different from the others because this is now a statement about fundamental classes of varieties. So firstly, if V is, sorry, if V is a smooth variety of dimension D over C, smooth irreducible, then we write square brackets V for the canonical generator non-equal of the 2D Borel-Moore homology of V. So in this case, where V is smooth, we can think of V as itself the manifold, and this is therefore isomorphic to the 0th cohomology group of V. And it's well known that for a connected space, this is isomorphic to C in the canonical way. You take your 0 cochain and evaluate it on a point. So So that's called the fundamental class of V. And now the interesting thing is that you can now do this for arbitrary varieties as well, or irreducible varieties. So if V is any irreducible variety of dimension D over C, then you can show that there's a unique element of the 2D Borel-Moore homology of V such that when you use the pullback to the open subset of non-singular points, you get the fundamental class that we've already defined in the previous point for the regular locus of V. So V has some singularities, but they form a closed subset, and the complement is this open subset, the regular locus. And you can show using the long exact sequence that I had on this board before that pullback in this degree is injective. So there's a unique, well, it's probably an isomorphism, I guess. So there's a unique fundamental class for V itself. And if you have an arbitrary not necessarily irreducible variety of dimension D, then it's a fact that this 2D Borel-Moore homology group of V has basis given by the fundamental classes of the irreducible components. So these VIs are the irreducible components of V. And in order to have this notation of fundamental class make sense always in this reducible setting, the fundamental class of V is just defined to be the sum of these fundamental classes of the irreducible components. I made a little mistake. It's not all the irreducible components, it's just the d-dimensional ones. Of course, in general, you could have irreducible components of various different dimensions. So it's just the ones which are the maximum dimension whose fundamental classes land in the right degree of Borel-Moore homology. So it's just those ones that give you that basis. And then the sum of those basis elements is what you define to be the fundamental class of V. And this is another nice advantage of Borel-Moore homology over a traditional homology, if you like, that it has these fundamental classes because you're not imposing the finiteness condition on your chains. The whole space itself figures in homology. Like in the example that I had before of C1, a one-dimensional variety over the complex numbers, the fundamental class of the whole space itself is there in the degree 2 Borel-Moore homology of the space. Okay, so Kevin just complained that that correspondences haven't actually appeared yet, so I better set up something for correspondences. So now let X1 and X2 be smooth varieties, smooth irreducible varieties of dimensions D1 and D2. And let Z be a closed subvariety of the product. Such that the projection maps from Z to X1 and X2, which I'll just call P1 and P2, are proper. So I've assumed quite a lot here, not all of which is going to be needed for what I'm about to say immediately, but This is the setup that we'll use in the application I'll get to. Algebraic geometers might call the variety Z itself a correspondence from x1 to x2. They might have slightly different assumptions that they wanted to make on these maps. But for us, we want to see the correspondence in homology. So we want to produce from this diagram a map from the Borel-Moore homology of x1 to the Borel-Moore homology of x2, except I think I'm actually going to want to put it the other way around. My assumptions are symmetric so far. So yes, I decided in the end to define it from x2 to x1. So from this, we get a correspondence in homology, which I'll call C sub square bracket Z from the ith Borel-Moore homology of x2 to one of the Borel-Moore homology groups of x1, but it's not degree preserving in general. It's I plus 2d minus d2. Now I think I said, okay, so Z is meant to be a d-dimensional closed subvariety of the product x1 cross x2. And this should be 2d2, sorry. So the way we get this is as the following composition. So you start off in the Borel-Moore homology of x2. Then you can pull back to the product x1 cross x2. Because the projection onto the second factor of the product is certainly locally trivial, in fact trivial, fibre bundle, and the fibres are these x1s, which I assume to be smoothly reducible varieties. So those are manifolds of dimension, a real dimension 2d1. So according to the pullback property, this should go to I plus 2d1 Borel-Moore homology. So this is P2 pullback. Then once you're in this x1 cross x2, where the variety Z lives, you can then take the intersection pairing in that ambient smooth space, x1 cross x2, and intersection with the fundamental class of Z, which lives in the 2d Borel-Moore homology of Z. And so according to the intersection property of Borel-Moore homology, this should spit out now something which is in degree I plus 2d1 plus 2d minus the real dimension of the ambient space, which is 2d1 plus 2d2. That Borel-Moore homology of, so now it's the intersection of x1 cross x2 and Z where this lives, so which is just Z. So of course the 2d1 cancels here. And so the final step then is to take the push forward map to I plus 2d minus 2d2, sorry, of x1. And this is now pushed forward through P1, which we assume to be proper, when restricted to Z, the map from Z to x1. So we've used the fact that it has push forwards, fallbacks, and an intersection form to define this. And this is morally, you should think of the first two steps as being the pullback from x2 to Z. It's just that the pullback properties in general don't allow you to pull back except through specific types of maps, which P2, we don't want to assume that P2 is locally trivial because it won't be true in the applications. So instead you pull back to a bigger smooth thing that this is sitting inside, and then intersect with the fundamental class of Z to actually land in Z itself. Okay, so in homology terms, it's this sort of map which is called a correspondence. Or maybe something slightly more general than this. because there's, it's important to point out that in this step here, it didn't really need to be the fundamental class of Z that you took the intersection product with. That's just one element of the relevant Borel-Moore homology group of Z. So you could, this definition would make sense if you replace this with an arbitrary element of that Borel-Moore homology group. So that's just a note. Oh, maybe I should have said one more. I think as well. Oh, well, I'll just say what I just said. So you can also define C alpha, a linear map between the same Borel-Moore homology groups. Forgetting the two. For any element alpha of the, you need the 2D Borel-Moore homology group of Z. Doesn't have to be the fundamental class of Z. So just replace the fundamental class with alpha in the definition and it makes perfect sense. So that'll be useful in a moment. The other thing which I should have said first is that if Z is the graph of a proper morphism from x2 to x1, I guess the way I've set it up, then the correspondence that you've got there is just the push forward through F. So this is generalizing proper push forward. So that would be the setting where the projection from Z to X2 was an isomorphism. So pulling back through that, well, pulling back to something bigger and then intersecting in that case would actually just not do anything. And then you just have the last step of the definition, which is the proper push forward part. So this is meant to and is generalizing the proper push forwards that you already have in the functoriality of Borel-Moore homology to a situation where you don't necessarily have a map between the spaces itself. You have this sort of correspondence, something mapping to both. Yeah, now there was a question remotely.
Oh yeah, sorry, Anthony, just a question. You're saying that these are called correspondences. Is that just the vocabulary or is there something to read into that?
Yeah, so Josh is asking about the definition of correspondence effectively. Yeah, so I mean, the correspondence is used to mean a lot of different things. Well, as I said, there's an algebraic geometry definition of correspondence in terms of the actual varieties. You know, so Z is a correspondence between X1 and X2 if you have maps satisfying some properties, and those properties would themselves differ from author to author. And so you could think of Z itself as the correspondence, but in other books, the word correspondence is also used for the induced map in homology, defined in this way. So you can also think of correspondences in the sense of the varieties as forming a category. You can compose those things that I've written there. So this ought to lead to some composition of these maps on homology. So suppose you have a situation where you have both X1, you have X1, X2, and X3, two consecutive pairs in this situation. So with a Z12 sitting inside the product of these that maps to both of them, and a Z23 sitting inside the product of these that maps to both of them. So Z12 is sitting inside X1 cross X2, Z23 is sitting inside X2 cross X3. and these satisfy the conditions that we had before. So in terms of spaces, the composition of these diagrams ought to be the diagram where you put the fibre product here. Sorry, I didn't let myself enough room. So where you have the fibre product here and those composed maps to x1 and x3. So that just the outer part of this diagram with that space, and that space could be thought of as the composition of the two individual diagrams that we had there. So it'd be nice if the correspondence in homology given by that outer diagram was related to the two individual ones. So now firstly, okay, so this is, so what I said is not quite right because this is not a subset of x1 cross x3. So instead, what is it? This fibre product So this starts off being a subset of x1 cross x2 cross x2 cross x3, but the fact that it's fibre product of x2 means that you can identify the middle x2 components and just think of it as a collection of triples in x1 cross x2 cross x3, namely the one satisfying the condition that x1 comma x2 lies in Z12 and x2 comma x3 lies in Z23. Okay, so another way to write this, which might be illuminating a bit later, is that this is the pre-image of Z12 under a projection which I'll call P12 and intersected with the pre-image under P23 of Z23. So here these projections are going from this triple product to products of two of the factors. So P12 is the projection onto the product of the first two factors, P23 is the projection onto the product of the second and third factors. Okay, so that fibre product lives here. What we really want for a correspondence from x3 to x1 or vice versa is something that lives just in the product of x1 and x3. So if we take the image of this space under the projection onto the first and third factors, then we get what's called Z12 composed with Z23. So that's defined to be P13 of this thing. Maybe I'll write it out in that second way because it's slightly nicer perhaps. Okay, I better continue on the other board. It's getting a bit too small. Yes, question here. Yeah.
So in note 1, are those maps also called correspondences?
Yeah, so Julian's asking the good question about whether more general maps like this would also deserve to be called correspondences. It's probably a matter of taste. I think so, because I'm about to show you that the composition of the two correspondences here is not a correspondence in the first original sense, but it is one of these. So if you want the composition of two correspondences to be a correspondence, then.
And also, is there, given like the map from homology to the homology of S1, is there like necessary specifications for knowing whether that is a correspondence for some?
Oh gosh, I have no idea about that. That's a very good question about how you can tell when a map from Borel-Moore homology of x2 to Borel-Moore homology of x1 is a correspondence for some z. Yeah, no clue. Okay, so write out again Z12 composed with Z23, then by definition it's a set of pairs x1, x3 in x1 cross x3, such that there exists an x2 in x2, satisfying the things before. The x1, x2 is in Z12, and x2, x3 is in Z23. Okay, so now this, if Z12 and Z23 happen to be the graphs of actual maps, then this would be the graph of the composite of the maps. So based on that special case, you might hope briefly that it might be true that the composition of the correspondences I defined is the correspondence for this space Z12 circle Z23. That's what the notation seems to suggest, but this is false. If you trace through the definitions, you see what the composition actually is. It's one of these more general correspondences with a class which is not a fundamental class of a single thing. It's what is it? So instead of the fundamental class of this, you take a class in the Borel-Moore homology of this, namely the push forward and the P13 star of, so essentially you translate the previous expression with maps in the definition of this space into something with push forwards and pullbacks in homology. So fundamental class of Z12, intersection in x1 cross x2 cross x3 with the pullback of Z23. So I claim that this is an element of, well, it's some particular Borel-Moore homology group of Z12 circle Z23. So it would be twice the dimension of Z12 plus twice the dimension of Z23 minus twice the dimension of x2. Sorry, I've written that too small. So you can check that it is an element in the right degree Borel-Moore homology of this space in order to define a map between the Borel-Moore homologies of from x3 to x1 in the correct with the correct degree shift that we expect. Yeah. So you can sort of see here what's happening, that the projection P13 from the actual fiber product to this space in the product of just two of the things is not an isomorphism in general. So there'll be fibers. In other words, for some of the pairs x1, x3 in this space, there'll be a choice of multiple x2s, so that they'll form a fiber over that point, and the homology of that fiber is then involved in this story by means of this. I mean, it will arise then in this in taking the push forward here. That will incorporate the fact that there are non-trivial fibers of the projection P13. Okay. I'm sorry I didn't lay that on the blackboard very well. Are there any questions about that, including questions about what some of the symbols actually say?
Sorry, Anthony, maybe what you just said implies the answer to this, but are there good cases where the two things coincide? You know, what would be nice and what is actually true?
Josh is asking about cases where this expectation is actually true. So as I said, it's true if these z's are actually just the graphs of maps from, if this is just actually the graph of a map from F3 to X3 to X2, and this is a map from X2 to X1, then this will be the graph of the map from X3 to X1, which obtained by composing them. And so in that case, it's true. So that's a case where the projection P13 from the fiber product is just an isomorphism. But essentially, I can't think of any other cases where that would be true. So, no other examples where this holds would spring to mind. So Kevin's asking if just one of them is an actual map. Yeah, that's a good suggestion. It sounds plausible. Yes. Yeah, I'm prepared to believe that, but I'm not sure that I can actually think it through.
So I think, Anthony, whenever you have maps with contractible fibers or acyclic fibers, you're going to have induced isomorphisms in homology, and then you get, like, for free, I mean, all of this becomes trivial because you can go up one of the arrows. Okay, so Vidit's suggesting that if you have maps with contractible fibers, then things like that might be true. So the only thing that worries me is that, after all, this is Borel-Moore homology, which is not homotopy invariant. Yeah. So
he said acyclic fibers.
Okay, acyclic fibers. Yeah, well, okay, probably, but then what is acyclic? Apart from a point. Yeah, okay, so there are interesting things to think about here, but I better actually start with an example and finish with an example.
But, sorry, just quickly, I think that Kevin's right, that if, as long as one of the z's is a graph, then then X2 is uniquely determined by the data of X1 and X3.
Okay, so Kevin, at least Emily believes that what you said is correct. Okay. All right, so I haven't left myself with much time to say illustrate this with an application to representation theory. So this theory is being set up for what Josh will say next week, the geometric construction of representations of Heisenberg algebras in terms of Borel-Moore homology of Hilbert schemes. But an earlier well-known example of correspondences in Borel-Moore homology being used to give a geometric construction of representations was Ginzburg's geometric construction of representations of the Lie algebra SLN. Using where the generators acted by correspondences in the sense that I've defined. In Borel-Moore homology of generalized Springer fibers. So all I want to show you is the SL2 case, because this will at least illustrate the idea in a where, the example where the spaces themselves are reasonably easy to grasp. So this is the example that I'll describe for the rest of the time. The SL2 case of Ginzburg's construction, and you can find the full thing in chapter 4 of Ginzburg. And there's also there's a paper on the archive by Jog Hamnitzer, which is very nice, which describes 3 different geometric constructions of representations of GLN, including this one. So in the SL2 case, the spaces that are involved in this are cotangent bundles of Grassmannians. So remember the notation that GA capital N means the Grassmannian variety, whose points are a-dimensional subspaces of an n-dimensional space. So this is a smooth projective variety of dimension, and irreducible, of dimension a times n minus a. And because I'm going to have to write that a lot, I'll call it d of an, which doesn't look much shorter, but it'll be shorter once once a starts becoming more complicated symbols. And we're going to consider the cotangent bundle of this, which you can identify with the set of pairs of a matrix and a subspace. So X is a linear transformation of Cn, and W is an a-dimensional subspace. And they satisfy the condition that X, the W contains the image of X and is contained in the kernel of X. So it's a little short calculation with tangent spaces to show that this is naturally identified with the cotangent bundle of this Grassmannian, but we don't have to know that, so you can just take this as the definition of this symbol if you like. It's this variety of pairs like this. And so now this is, as would be suggested by calling it a cotangent bundle, it's still smooth. It's a vector bundle over GAN by the projection of forgetting the map X. And so this is no longer irreducible. So as a space, this is not compact anymore. It's got a vector part, but it's a smooth irreducible variety of dimension twice the dimension of the Grassmannian. So now what I want to define is an action of the Lie algebra SL2 on the direct sum of the homologies of all of these Grassmannians for a fixed n. Yes, the Borel-Moore homology of the cotangent bundles of these A's. And I want the subspace where you fix A to be one of the weight spaces of the representation. And I'll make it the 2A minus n weight space. So what that means is that I need, so in the standard basis of SL2, call it EH and F, H is going to give you the weights and E will raise weights by 2 and F will lower weights by 2. So I need a linear map from the Borel-Moore homology of the Grassmannian with AN to the Borel-Moore homology of the cotangent bundle of the Grassmannian with A plus 1n. Well, so E is meant to go up like that and F is meant to come down like this, and they have to satisfy the property that the commutator of E and F, when restricted to the weight space with weight 2a minus n, is 2a minus n times the identity. Okay, so the point of what I've been saying is that we're going to construct these linear maps in homology as correspondences. So we need some suitable subvarieties of the direct product of this cotangent bundle and this cotangent bundle. And we're just going to write down the most obvious condition possible on a pair of an element in here and an element in here. So the elements in here and elements in here are themselves already pairs. But if you just write down, I mean, the first thing you would think of is what we're going to use. So let Z A plus 1 n be the set of, this is meant to be a subset of the product of those two cotangent bundles. So it's going to be a quadruple initially of x, w, x prime, and w prime. And we want to impose some conditions, some relationship between the two things. And so the most obvious relationship between x and x prime is that they should be the same. And we can't impose that w and w prime are the same because this is a-dimensional and this is a plus 1 dimensional. But the next best thing is that w should be contained in w prime. So that's the most natural incidence variety between these two things. And you can show that this is actually again smooth, which is not something you actually need for the construction, but it's just a nice feature of this case. This is smooth and irreducible of dimension. Now it's exactly the average. Well, it's the sum of the complex dimensions of the Grassmannians involved. So it's the average of the complex dimensions of the cotangent bundles involved. So it's exactly half the dimension of this whole product, which might make you think that there's a symplectic story to say here, which is true, but I won't get to that. And you need to check that the projections from this space to the two cotangent bundles are proper. But that's okay because they're projective morphisms. And it's crucial there that we've imposed the condition that x equals x prime, so there isn't any remaining vector part floating around. That if you take a point here, for instance, that consists of a pair of x prime and w prime, so its pre-image initially is a set of quadruples like this, but x is forced to be equal to x prime, so that's not actually a choice. It's only the w part which is a choice. And so in that case, you'll see that the fibre is a projective space. And more generally, you can see that this is a projective morphism. Okay, so we're all set up there in the way we had before. we've even got the bonus that Z itself is smooth, but that's just a nice extra feature. So you let F act by the correspondence defined by this Z, A plus 1 N that I've defined there. So that'll go from the ith Borel-Moore homology of the cotangent bundle of G A plus 1 N to the Borel-Moore homology in some degree of the cotangent bundle of G A N. So if you trace, if you plug in the dimensions that I've written down in the general definitions, you get the answer, which I can't again remember. It's I plus 2 times the difference, 2 times dAn minus d A plus 1 N. And you let E act by just the reverse thing. So it's really the same variety, but if you like, you can define Z A plus 1 A N to be exactly the same thing, but with the factors swapped so that the ones relating to A plus 1 come first, and then it would go in the other direction. So now it would be I plus 2 D A plus 1 N minus D A N. Okay, and then so then the claim is that the commutation relation between E and F that I had before is satisfied. So since this is a statement about EF minus FE, you need to know how these correspondences compose, and that's where you use the formula that I gave before. But unfortunately, I'm not going to have time to go through the proof. So this is said in the book by Christian Ginsberg, chapter 4. Okay, so something which I probably also can't prove. So that's claim 1. And then claim 2 is that you get the irreducible representations of SL2 as natural sub-representations of these. So if you just take the Borel-Moore homology in degree to dAn, so if your degree is 2 dAn here, then clearly you'll land in the same degree for the A plus 1 thing here when you apply F. Oh, that was E, and similarly for F. So this subspace with these particular degrees is SL2 submodule of the whole thing. And the claim is that this is the irreducible representation of SL2 with highest weight n. Now, this, I mean, if you believe the first claim, this is in fact almost obvious because all you need to check is that each weight space is one-dimensional, and then there's only one SL2 representation with one-dimensional weight spaces in the right degrees. So the reason this Borel-Moore homology group is one-dimensional is that because this is a cotangent bundle, this is a vector bundle over a GAN with fibers of dimension DAN. You can show using the definition we had before that this is isomorphic to the Borel-Moore homology in degree 0 of GAN, not the cotangent bundle. So there'd be a map from here to here, which is the pullback under the projection from this vector bundle to its base, and that would be an isomorphism in this case. And GAN is projective, so this is just the same as ordinary homology. So in particular, it's one-dimensional. So I think I'll stop there, and I'm sorry not to have got to any of the calculations which prove, for instance, this commutation relation. The idea is that Josh next week will be talking about a similar result proved in afterwards by Nakajima and Granovsky, which gives you a similar way of geometric representation of the Heisenberg-Lie algebra on homology of Hilbert schemes rather than homology of these sorts of Springer fiber type things. So anyway, we'll see more of the composition of correspondences there and how these calculations actually work. But for today, I better stop. Thank you. Are there any questions either here or remotely? Julian's got a question. Yes, so as far as I'm aware, this sort of construction is a type A thing. So what would change? So Nakajima generalized it in some sense to give geometric representations of general Kac-Moody-Lie algebras, or symmetric Kac-Moody-Lie algebras with a symmetric Cartan matrix, at least. So ADE type and so on. But so that's using the cohomology of Nakajima quiver varieties. But I guess in type A, that would become that would recover this construction, but that uses so in principle, it's known that Nakajima quiver varieties in type A are isomorphic to generalized Springer fibers and these sorts of things by a theorem of Maffei. And the whole motivation for that was the idea that Nakajima's construction in type A ought to be the same as Ginzburg's construction. And I'm not sure that all the details have actually been worked out to justify that statement. Yeah, so I guess I should have given the answer yes, but I mean, yes, it can be generalized to other types in the sense of Nakajima's constructions for symmetric Kac-Moody-Lie algebras. But it's maybe not totally clear that it really is the generalization rather than something similar but slightly different. Anna's asking about the history. I mean, I feel like Ginzburg's construction would have been after the early papers on quantum groups, so maybe the 90s. Yeah. So of course, maybe I should point out that constructing the irreducible representations of SL2 is not remotely impressive. They're incredibly easy to describe. So really the point is to give a construction of irreducible representations of SLN where you can then actually genuinely translate some questions that you might not be sure about into geometric terms, and that may or may not help in answering them. But it is at least. Okay, so one other thing I should have said, so if I'd given the definition for SLN, this would have been clearer, but at least I suppose I can talk about it for SL2. So this vector space is not just one-dimensional, it has a canonical basis vector. I mean, this is the 0-degree homology of the space, so there's a canonical basis vector there. So this gives you a canonical basis of the irreducible representation of SL2 with highest weight n. And okay, so again, that's not particularly impressive, because even just from the combinatorics of irreducible representations of SL2, you can sort of see what the most symmetrical basis to choose is. And that's the one that everyone had been using well before these geometric constructions came along. But for representations of SLN, having canonical bases is a big deal. And Ginzburg's general construction does give, so now I shouldn't say canonical, I should say a particular choice of basis of any irreducible representation of SLN. And for a few years at least, there was a hope that it was equal to the canonical basis that Lustig had defined, that Kashiwara and Lustig had defined. And that turned out, unfortunately, not to be the case. And it's now well understood in geometric terms why it's not the case. It was falsified by a counterexample of Kashiwara and Saito, where they found an intersection cohomology complex on a Schubert variety, which had an interesting characteristic cycle on a Schubert variety of type A, with a characteristic cycle with coefficients bigger than 1, and that caused a divergence between Lustig's canonical basis defined in terms of perverse sheaves and his canonical basis in homology defined, which is defined in terms of fundamental classes of irreducible components. I'm not sure. I mean, if Geordie was here, he would know this, but I think sort of the order of SL8 or thereabouts.
Kashiwara Saito is in the flag variety of SL8.
So Peter's saying Kashiwara Saito is in the flag variety of SL8. Yes, so then you have to translate that singularity into a singularity that occurs in here. Yeah, Peter, do you have any thoughts about where it would land if you translated it into Ginzburg's geometric construction of representation?
I haven't tried to translate it.
Okay, so Peter hasn't tried that, so yeah, so I might be remembering the wrong SL8. We won't get into that. Okay, are there any other questions?
Anthony?
Sorry, I've got two questions happening. So Anna first, maybe. Oh, yeah, Anna's pointing out that I shouldn't say it was disappointing that there were two different interesting bases for these representations. Maybe in a sense it's better. Yeah, okay, fair point. Yeah, that's right. That's true. I guess that, yeah, it would have been great if we could have said canonical basis and meant and that there was really only one, but yeah, sorry, now it was Josh that had a question remotely.
Oh, no, it was me, Kaylin.
Oh, hi, Kaylin. Hi.
So, how does one realistically compute what the map is from the correspondence?
How do you compute?
Like, so
well,
we have a definition, but how does one realistically compute? Like,
okay,
you do a lot of things.
Yeah, so if I'd had 20 more minutes, the easiest computation that I could have done would be to take these one-dimensional spaces with their canonical basis vectors and show you what the correspondences do on those at least. Because for the canonical basis of SL2, you want E and F to act with certain specified coefficients. And I could have shown you how the correspondences do produce those coefficients. They end up being the Euler characteristic of certain fibers involved in the diagrams. So so all that would have verified is that you can have a hope of computing the correspondences if what you plug in is itself the fundamental class of something. Yeah, so that's something at least, but it's not everything. But in general, if you have a basis of your homology given by the fundamental classes of sufficiently nice subvarieties, then you might be able to compute the correspondence explicitly in that basis.
Can you say a few words why Euler characteristics show up?
Euler characteristic shows up because at some point you have to take an intersection pairing somewhere, and so you're counting points, and Euler characteristic shows up when you're counting things. I mean, it's so I said Euler characteristic rather than a count of a number of points, just because it's more convenient to do the calculation in some fallback space where your intersection is not zero dimensional anymore. Yeah, so I don't think I have anything more intelligent to say than that.
Thanks.
So that's another calculation which you can find in Ginsberg's chapter 4, Chris Ginsberg, chapter 4.